Bueno, yo voy a hablar en inglés por si hay alguien que no esté viendo o que esté por aquí, que no pueda entender todo el español. There are many parameters affecting or accounting for the quality of astronomical sites. The water vapor content is the main parameter affecting the infrared conditions in astronomical sites. High levels of water vapor reduce the atmospheric transmission and also increase the thermal in the infrared background. It is assumed among the astronomical community that sites located around 2,000 meters above sea level are not suitable for high-quality infrared observations. However, the evaluation of the infrared quality of the Observatory del Teide here in Tenerife and the comparison with prediction models indicate that the Teide site at 2,400 meters above sea level could be as good as Mauna Kea for infrared astronomy. In this plot, we can see the transmission spectrum measured at the Teide Observatory and the spectrum from a model for a place located at 2,400 meters. And we can see that the measured spectrum is much better than the prediction. When we compare the measured spectrum with a model for Mauna Kea at 4,200 meters above sea level, the agreement is now much better. The proper characterization of the precipitable water vapor, it is important to evaluate the infrared quality of the Roque Muchachos Observatory, a site candidate for the ELT. Temporal fluctuation of this parameter strongly affect the quality of the infrared data recorded at the ground-based telescope. And the fraction of night presenting good infrared conditions as a function of the epoch of the year will allow to optimize the scheduling of the telescope observing time. Measurements of precipitable water vapor can be obtained in a number of ways, from in situ measurements using radiosound to remote sensing techniques such as photometers, radiometers, global positional system, GPS, spectroradiometers on satellite, etc. All of these techniques have their own intrinsic uncertainties in an order of about a few millimeters. The site testing group here, as García said before, has been exploring the use of GPS with Soluciones Avanzadas Canarias, a private company, the use of GPS measurements to estimate the precipitable water vapor at the Roque Muchachos Observatory. And now Ignacio is going to explain the procedure to estimate the water vapor from this technology. And after him, I will present some statistical results.
Okay. Thank you very much. I'm very happy to be here. I am not a scientist, so that's important because sometimes I like to do things because they are engineering puzzles, and sometimes GPS processing is like an engineering puzzle. The underlying reasons are sometimes not very clear to me, so working with scientists such as the ones here is a real pleasure because it illuminates the conversation a lot more. I'm going to talk about specific work that we have obviously done together. I've only concentrated on the part of the GPS data processing. GPS data processing is a very well-established technique. What we do is that we take permanent stations. These are not roving receivers. This is not a receiver in your car. This is a receiver that's permanently placed in a specific location. And in particular, the antenna itself has to be permanently fixed to the ground or to a permanent structure where it is unlikely to suffer from high winds, movements, or anything like that. So we are trying to record using the antenna and the specific receiver measurements to the GPS satellites. Those measurements, as we will see, are actually distances to the satellite. As we record very long passes of those satellites overhead, we can infer many things about the medium that the signal crosses. And also we can infer what's happening to the actual station itself and to the satellite. So it serves as a continuous monitoring system for a location. In geodesy, it's a very well-established technique where permanent stations such as this one in La Palma, there's about 400 to 1,000 publicly available, are monitored every single day to determine tectonic plate motions over long time series, and also landslides, volcanoes, earthquakes, tsunamis, etc. It's a technique from geodesy that's very well established. The station in La Palma belongs to the IGN, to the Instituto Geográfico Nacional de España, and has been established since 2001. It is a very well-performing station within an international network called UREF. It's also, since about 2 years, a part of the international network of stations called the IGS. And the station is very well run and maintained already by the IGN. It is used for the establishment and the maintainability of the UREF reference frame, which provides a continuous reference frame within the whole of the European continent, trying to unify all the different reference frames of all the nations. So the station is obviously in a location that you know. It is up there close to the observatory. And it is of interest in this kind of work to see whether the station has been performing okay. And this is only just to show that, yes, the data has been coming in. The data availability is close to 100% all the time. There are some days where we don't have 100% of the data. That's why we cannot calculate the precipitable water vapor for those days. So it means if we don't have data, then obviously we can't have precipitable water vapor. But for the majority of the period that we have looked at, the data is, sorry. The data content is at 100% or so, and also the data availability over the years, the number of files, there should be 1 file per day basically, is very close to 365 as expected. So that's the first thing that we have to concentrate on, because all these studies are based on having continuous data from reliable stations. And nothing about this technique works unless you have a continuous station that's well maintained. Nothing like bad data to have bad results. So here we have shown that we have good data. Now GPS data processing is simple. The principle behind GPS operations is that an encrypted signal is transmitted from the satellite below the noise level, and then through correlators we can extract the actual message that was transmitted. The message itself carries no information, so instead of bits we call it chips. And the message is relatively long. It can be up to 1 millisecond long or so. And then we do a matching between what's emitted from the satellite and what we reproduce, because the code itself is public, what we reproduce in the receiver. Now the transmission time, which is the difference between the receiver time and the transmission time, multiplied by the speed of light, gives us a distance. Okay, so that's the basic GPS fundamental equation. How long did the signal take to get from here to there? It's the same thing that we do with a lighthouse for the ship travel, or that we do for many other things. So the interesting part is what happens during this transmission part. So obviously we can assume the speed of light at vacuum, which is convenient. That's not something that we're going to touch. What we do basically is we start complicating this equation. Times are not actually synchronized, so the time of transmission is not exactly in the same time scale as the time of reception, so you have to account for that. That's called clock bias. There's a receiver clock error and a satellite clock error. And also this distance itself is affected by atmospheric delay, which includes ionosphere and troposphere, both, and some other errors. So it's a little bit not so clear here, but we have basically clock error from the receiver, clock error from the satellite, or differences in time scale. And also we have the atmospheric part, which is what we're interested in now. Now, traditionally in GPS data processing, the atmospheric part is considered an important but a fundamental correction error, but one which has not been developed as well as some of the others. For example, some of the errors that go in here have to do with the antenna calibration. Every antenna, as you well know, has a phase center. Anything that receives electromagnetic waves does not see them the same whether they are in a certain elevation or a certain azimuth, because they're active components. So this antenna phase center may vary within 5 millimeters. We have, through anechoic chambers and through field calibrations, calibrated the antennas to within 1 millimeter, all of them. On the other hand, a lot of people have assumed that the atmosphere behaves in a very predictable way, which is obviously not the case. So what has been happening within geodesy is that as we improve all the models that go behind clock estimation, the atmosphere has gotten a lot of more emphasis. And there's where we have reached the conclusion within this study and other studies by other scientists, that we can indeed be so good that we can predict or we can estimate with great certainty what the precipitable water vapor is from the atmosphere using the characteristic of the GPS signal. Okay. Here what we have, this is nothing but the phantom, so we assume what the distance must be to the satellite. Now, to assume a distance to that place is, in this case, the satellite. The satellite itself is moving at about 3 kilometers per second, so it's not something that you can easily know. So therefore, we rely on external providers of orbits. The orbits themselves come from an international project called the IGS, which I'm also involved in. And the IGS publishes orbits that are within 1 to 2 centimeters precise. So you have very good knowledge of the center of mass of each satellite as it flies around the Earth. Now, this is essential so that we can then extract any useful information from the atmospheric delay. The atmospheric delay, which is really just how much longer appears the path than the vacuum path. So we assume we have vacuum, assuming no atmosphere, and then we should be seeing a straight geometric path. But the truth is that obviously the signal does some things within the atmosphere. We're not going to reproduce all the things that the signal does, because it is, in any case, too computationally. But what we do is that we reproduce this complex physical characteristic with an extra name to account for the atmosphere. So we say, how much longer did the signal take, or how much more distance did the signal have to travel because it had to cross the atmosphere? Why? Because otherwise we would have to use several different speeds of light, and we would have to be accounting for when it crossed a layer of the atmosphere and when it exited, and all those things become too complicated. So we are basically with the tropospheric delay, which is what we are using, as one value as the column of water over the atmosphere in the zenith direction. Okay, but actually no satellite is in the zenith direction. It is very unlikely that a satellite passes directly overhead, and even if it did, it's only there for a few minutes. So what we're doing is actually all the ray traces, all the actual lines that are coming to the satellite, if we could imagine that in our head, to the antenna from all directions, from all GPS satellites. A GPS station in La Palma may be seeing and recording data from up to 16 satellites at once. So you have many different azimuth directions and many different elevations. We map, there are mapping functions, very well established mapping functions, that map all those delays onto the zenith direction. And that is the value that in the end we have to estimate. There are certain caveats to all this. I'm doing a summary, obviously, but this is the essential. We cannot, within the least squares, estimate one parameter per satellite and then somehow in the end bring them all together. What we do is we only set up one parameter per station every 2 hours. So we're doing not only a summation of all the ray traces within a particular time period, we're also summing over time. Why? Well, because the weather in general, as such, does not generally change that quickly. And so within geodesy, it has been assumed for a long time that 2 hours is a reasonable average in time. Now, it is quite easy to push this to 1 hour, and we have done that as well within the study, and it shows very good results. But 2 hours was the initial period, and what we have validated so far, and it works okay. The elevation-dependent mapping function, like I said, relates all the measurements in the estimation bin in that specific part to the TZD, to the tropospheric zenith delay parameter, and that's it. And therefore, we only estimate one TZD because the mapping function has no estimatable parameter. Then it's a given. All the TCD values in this runs were estimated, initializing at 2.1 meters. This is quite common, that if one is to assume that any station in the world has a delay of about 2 meters, or an extra length that the signal has to cross or be transferred, the parameter of 2 meters more or less works. This is actually what most handheld receivers assume. They just have a built-in delay. They know that the signal will travel at 2 meters more than normal. Now let's think about this, because a GPS satellite flies at 20,000 kilometers. So we're only adding 2 meters to 20,000, but that's enough. And we can recover useful, scientifically valid information about the system. Now, in La Palma, actually it's never 2 meters. It's always 1.8, 1.9, and it fluctuates in there. And so the system itself, the least squares, has to find that 1.8. But of course, if you put 0, then by the time it gets to 1.8, you end up with too many iterations, so we start at that level. The system, so that we don't propagate errors, what we do is we estimate each 2-hour bin independently and create step functions. So as soon as that 2 hours is discarded, then we start with a new estimation. There are some people that do linear estimations. But what can happen is, obviously, if you have corrupted data within several bins, then they can corrupt the estimations in between. That is really just a decision in the estimation process, but it can be changed. So, sorry, this looks really dark. The tropospheric zenith value is not what the IAC was looking for, but that's what I calculate. There's an extra step that needed some development within my company, which was to actually get from the tropospheric zenith delay the precipitable water vapor, which is what we call it, precipitable water vapor based on GPS. The tropospheric zenith, the delay due to the atmosphere has to do, or has two major components. One is the ionosphere, which is reduced almost completely to 98% using the ionospheric combination of the observable. That's just a given, and let's take it as such. So we assume that the ionosphere up to 98%, first order approximation is up to 98%, it's okay. But the second part, which is harder to characterize, is the actual wet part of the atmosphere, which is from 0 to about 30 kilometers or so. And within that, we have also two, the dry component, or the hydrostatic, which has to do with the inert gases, and the wet part, which has to do with the water vapor. The hydrostatic delay, which we call ZHD, zenith hydrostatic delay, is actually based on model, or at least it's, you can parameterize it with respect to the local pressure, the height, and the latitude of the station. Of course, this value you can see is very small, and this one is very small as well, much smaller. So there's a lot of researchers who just take all of this out because the input. We have left it in, and we find that it's a useful approximation to be as complete as possible. But the pressure becomes very important at the site where you're measuring it. So we take this, and now we know what the zenith hydrostatic delay is. We can take that out, obviously just a simple subtraction from the tropospheric zenith delay, and now we're left with the zenith wet delay, okay? But what has been found and corroborated over time is that there's a proportionality factor that depends on temperature, between the zenith wet delay measured at surface, or where the station is, with respect to the precipitable water vapor that's in the column above the station. There's a proportionality because obviously the pressure that you're measuring is at that location, and you're interested in a range of heights. So that has to do with the average temperature over the column, which is related to the surface temperature. The surface temperature is related to the median temperature of the column of air, and also has to do with the Reynolds number of air and the density of water and all kinds of things. But this is very well established. Now this value is actually around 0.15. So there's a proportionality of about 0.15 depending on the temperature. And then now we can get the precipitable water vapor based on GPS in millimeters as a distance as well, okay, which is how we like to calculate it. And I think I'm done. So basically, before Begoña comes, this is where we stopped. We basically were able to get precipitable water vapor estimation based on GPS, on continuous operating GPS stations that can work at night and day, whether it rains or it's shining, it doesn't make any difference. The station has been confirmed to be of very high quality, and the precision of the calculations is very high. we're getting an RMS of convergence in the phase measurement, which is a measurement that has about 19 centimeters in the wavelength of less than a millimeter, the convergence of all the measurements. The calculations have also been done because it can happen sometimes that a station, when it's isolated, can have certain biases within itself. What we have done is we have put it in a network of stations. I didn't have a chance to prepare the map for that, but basically the station, when we make calculations, is within a network so that all the satellites are visible in every single estimation. Although La Palma cannot see all the satellites, obviously, because it's in a specific part of the world, we take into account basically all the orbits of all the satellites, so that when a satellite comes in and out and is visible and not visible for La Palma, we have some estimation from other places, such as Mauna Kea, or such as stations in Africa, or in Madrid, or in all over the world. We have used up to 25 or 30 stations, every processing run, where the important part was La Palma, but all the other stations are there to keep coherence within the whole estimation process. Because as you know, least is unstable if you don't have any calculations. So, anyway, more, thank you.
Okay. In order to validate all these calculations, we perform a direct comparison of the GPS estimation of the precipitable water vapor with radiometer measurements. The radiometer measurements were obtained in the period from June 2001 to July 2002 during the GTC site prospection. And we found a linear relationship was determined using a Bayesian approach, taking into account the uncertainty in both estimations. And here we can see the best fit and the residual to the best fit. And the standard deviation of these residuals was 1.53 millimeters. Just for comparison purposes, we performed a similar study for Mauna Kea. And to validate the GPS estimation of the precipitable water vapor in Mauna Kea, we use data from the Caltech submillimeter observatory, in particular opacity at 225 gigahertz. We performed a similar validation, and the final standard deviation of the residuals was 1.58 millimeters. From the processing of the GPS data, we finally obtained this time series for the precipitable water vapor at La Palma site with 2-hour temporal resolution from June 2001 to December 2008, but we already have data from 2009. And here we can see the fraction of the for which the precipitable water vapor was found to be below a given value, the cumulative distribution. And this is the full time series for Mauna Kea with the same temporal resolution as for the same period of time and its cumulative distribution. The dotted line here corresponds to the uncertainties due to both the measurement and the calibration. Well, GPS provides precipitable water vapor estimation in almost continuously, and unlike other techniques, in almost all weather conditions, including those of local fog, clouds, dust, or whatever. Well, from the time series, we have derived the global and seasonal statistics of the precipitable water vapor, and here we have the results. The average, the global average precipitable water vapor at La Palma site is 4.83 millimeters, and the median value is 3.79 millimeters. We found clear seasonal differences in the precipitable water vapor statistics. The lower values correspond to winter and spring, and the largest during summer. In this table, we include the percentage of night time the water vapor is in a determined rate, in this rate. and approximately 39% of the night time presents precipitable water vapor smaller than 3 millimeters, which corresponds to good or excellent conditions for infrared astronomy. This percentage increases to more than 52% of night time to obtain good infrared observations or high quality infrared data at La Palma site. Okay, in this part I include the statistics for Mauna Kea, also derived from GPS data, and we found that the global average precipitable water vapor at Mauna Kea is almost 2 millimeters smaller than in La Palma, which is not surprising due to the large height difference between both sides. But it is important to note that the median value during winter and spring in La Palma are similar to the global median value at Mauna Kea. Okay, we have derived the monthly average precipitable water vapor for any month and any year, and for the full time series, in order to study in detail the seasonal trend of the precipitable water vapor. And, well, we found a clear seasonal behavior of these parameters, which does not differ significantly from one year to another. September and April are the worst and best months in terms of precipitable water vapor in La Palma. This is the same plot for Mauna Kea, where we don't find a clear seasonal behavior of the precipitable water vapor. The statistical values are almost the same for any month, although we found some strong differences when we compare different years. Okay, we have also calculated the percentage of time in which the precipitable water vapor is smaller than 3 millimeters that correspond to good conditions for infrared astronomy. And we found that this percentage also varies along the month. During February, March, and April, more than 60% of the night time present good conditions for infrared observations in La Palma. And even in September, the worst month in terms of precipitable water vapor, around 10% of the night time is highly appropriate to obtain high-quality infrared data. In this sense, La Palma is a good site to obtain, to carry out infrared observations at any time in the year. But of course, February, March, and April are the best months for that. This is the same plot for Mauna Kea, where more than 60% of the night time present good conditions for infrared astronomy for almost all the months. When we compare both plots, we can deduce that for each 10 hours, 10 useful hours for infrared astronomy at Mauna Kea, La Palma will present 6 hours in average. This number is only 3.9 and 4.7 hours during winter and autumn for each 10 hours of useful conditions for infrared astronomy at Mauna Kea. But during winter and spring, La Palma will have 7.9 and 7.4 hours for each 10 hours of useful conditions for infrared astronomy at Mauna Kea. Okay, other important property of any parameter is the temporal stability. We have calculated the average temporal range in which the precipitable water vapor are stable under a determined value. If we fix the 3 millimeters, the limit for good conditions for infrared observations, we found an stability of 16 hours in the period from 0 to 3 millimeters. And this number in Mauna Kea is, the corresponding number is around almost 24 hours. There are differences, but at the end, in both sides, this number indicates just a full night. So the precipitable water vapor at La Palma and Mauna Kea is almost the same and is not more than a full night. Okay? And to conclude, just to summarize the statistical results, the median precipitable water vapor at La Palma is 3.79. This parameter presents a clear seasonal behavior, and winter presents the lower statistical value with a median value of 2.82 millimeter, which is comparable to the median value, the global median value at Mauna Kea. More than 60% of the night time present good conditions for infrared observation during February, March, and April. And for 10 hours of good conditions at Mauna Kea, La Palma presents more than 7 hours during winter and spring. And the temporal stability presenting good conditions for infrared observation is comparable at both sides and is around a full night. And that's all. Thank you.
Thank you to all of you. It's been very nice.
What is the reason why, when one would expect that the precipitable water vapor is higher, like in winter, okay, than is where we have low pressures? What happens in the atmosphere to make this value lower in winter than, so to do the nights better in this sense during the winter than during the summer?
The same reason, because you expect a good thing during summer and worse in winter. It's a methodological reason.
But the amount of water vapor that the atmosphere can have is very related to the temperature. So the lower the temperature, because otherwise it will condensate at the superface. So you cannot keep it not pressure. And water obviously is very much. Then you can see that the colder atmosphere, which is the reason why at higher altitude have less water. And why I see that you see that back in the temperature. I think I should do just with the temperature of the atmosphere. It cannot hold that much water vapor. We have some more correlated granular.
No.
But that could be the thing that we haven't before that comparison.
One thing that I'm not sure I understand is when you say precipitable water vapor at La Palma, how many satellites in one day are you using? And I guess you're looking at hundreds of paths in all directions. So it's not an average on top of your observatory. It's really on a very large area around your observatory, right?
The visibility of the satellites is perfectly massive. I mean, there are no blocks of the signal at La Palma. Because the station is set on top of a 1-story building, pretty good sized building, so there's no connection in the building. They put it on top of the building. It may see, thank you. It may see anywhere between 16 and 24 different satellites. But a pass of a satellite at that latitude can last between 6 and 12 hours or something like that. I mean, you can have really long passes where the satellite is with you for a long time. So basically, what the mapping function is what allows you. These are obviously they are empirical mapping functions, but there's a mapping function for the dry part and a mapping function for the wet component. And the mapping function allows you to parameterize all these ray delays into only one value at the zenith. It's like I said before, it's not that any satellite specifically is going at the zenith at that time, but rather that the summation of all the satellites that you see over 2 hours, which is a lot of data, we have found, you can see it in the RMS of the calculation, that it is enough. I mean, it is very good to characterize the atmosphere. Okay. There is only one other thing that people may do, which is sometimes to characterize the mapping function by one estimated value over those 2 hours as well. But we have found that can also lead to instabilities because the mapping functions are empirical in them. If you allow too much variability within your least squares, you can end up with numerical instabilities just out of So you have to be careful within any estimation process, especially when all the underlying physics are not well known, that when you do the partials, obviously, and all this, that you don't introduce numerical problems because you have way too many parameters. So we have found that you take all the satellites that you can see in the sky. We do these calculations every 5 minutes. So the epochs, we take all the measurements every 5 minutes, and then every 5 minutes. So imagine, in 2 hours, there's a lot. And it can see up to 16 satellites at once. So every 5 minutes, 16 measurements per satellite over 2 hours. So
it's just, I saw one of you commented that the differences between La Palma and Mauna Kea may be due to height. But the GPS was not, the GPS in La Palma was not at the Roque, right? Or did I see wrong the map?
No, the GPS in La Palma is in the...
Well, in La Palma is near the residencia.
Oh, so it's at the... Okay, all right. It's just I saw a different map. The other question is, you show... yeah, on the very first slide.
Here.
Oh, it looked like it was... Oh,
this here, that's, you may know these buildings. I've never been there, so...
The last one is the residencia, and the talleres, and this is the...
Yes, I was confused. I thought it was...
The helipad.
So the other thing is that you show a very nice graphic where you correlate with satellite data. And I think this is very easy to get for 1 year. But the crucial thing when you want to do, not for astronomy, but when you are interested in climate change, and humidity is a key factor for climate change. When you compare with satellites are in a very dangerous environment and they suffer from trends. So one thing you should really estimate is how accurate your measurements are and how long can you detect trends over a decade or 2 decades. Because with the grid of stations with GPS of the world, you can beat the satellites. I guess I'm pretty sure you could get more precise long-term measurements than satellite data do.
Yeah.
And one thing that...
What happens to the... You mean that the satellite itself puts an error within the time series?
That you put the satellite in space, and basically they're all absolute measurements. They rely on radiometers, right? And the instruments degenerate. The filters they use, they get...
Yeah, but I mean, in this case, but you mean that people that measure precipitable water vapor with satellites?
Yes.
But that's not what we're doing. We're using... Yeah,
I'm saying you can beat them. You can do better than them.
Yes.
With your method.
Yeah.
And one thing which is important is related with the first question is not what you're measuring is the absolute water vapor content in the atmosphere, but towards the formation of clouds, and this is related to the temperature, but towards the formation of clouds and albedo and all these parameters, the important thing is relative humidity, which is related to temperature. And you know the temperature, so you could get relative humidity from your measurements too, and that would be very, very good. Okay, I'm done.
So that's something we could consider, to publish the relative humidity.
Can you show the correlation plot, the one? Yeah, I mean, I see a gap in the data. Is this related to any specific... yeah, here, exactly.
Yes, the reason is that the radiometers, well, the radiometer measurements were obtained during Ultra. So, most of the measurements are also in Ultra, and some of them not in the back of it. Because they the news when the radiometers happen to track, the mouth, the nuclear,
What is the spatial scale of variation for this parameter? You don't know if vary in kilometers or meters?
We don't know the spatial scale for this parameter because in this process, even though I included many stations, we actually didn't get the time series, and La Palma only has one station, and the closest station for this time period is Maspalomas, which I did process, and I did provide the precipitable water vapor, but precipitable water vapor has so much to do with the height. Maspalomas is only at 200 meter over elevation, that it has nothing to do with each other. So we know for sure that 250 kilometers between La Palma and Maspalomas is not right. I'm pretty sure that within the same height level, it is quite stable over, at least with this technique, because we're seeing the same satellites crossing the same atmosphere. But as soon as you moved lower, then you're concentrating a lot more water vapor at lower heights. And so, of course, this is critical here from 0 to about 8 kilometers, which is where most of the water vapor is. So if your 0 starts at sea level and there are humid conditions, then of course you're going to have more. But it's got more to do in other words with height than it has to do with actual spatial. So I would assume, and this is a speculation right now, that a similar height station within the Canary Islands will have similar conditions to La Palma. But that's something I don't really know for sure.
There are some studies.
Effects, but it could be other causes of such a delay that can introduce some noise or some error on the measurements.
Yeah, the troposphere is obviously where climate happens, where weather happens. So I'm not, like I said in the beginning, I'm an engineer. This means I'm not a meteorologist, but for our purposes at least, and for the stability of the least square system and for the convergence of a system that has hundreds of thousands of measurements, it is useful to characterize the troposphere as only two layers, a hydrostatic, or two components. A hydrostatic one with all the inert gases, and then just another part that we call wet, but it's really where the water vapor is. It's more than that. So it is quite likely that there are more things going on. I'm not disputing that, but I'm not sure that any technique can really separate those things. And definitely ours cannot. I mean, or you can add more layers and more complexity to the system and still keep it stable. But I'm not sure how relatable it is to the actual underlying physics. And it gets to a point in all these estimation systems, as you probably know, where numerical fancy work can simulate real effects, but they're really just numerical things that work and not necessarily things that represent physics behind it. So this happens sometimes because all the observations are seeing the same satellites at a particular height, or they all have some common effect. And you have to always be careful that the underlying models that we're using have something to do with real life. And this, I have to say that sometimes it's not easy. We have found it within the satellites themselves. We actually started this work as part of characterizing the way the satellites behave in their orbits. And there we have to account for many different things that we didn't think before. And albedo effects from the Earth, infrared radiation from the Earth, which displaces the satellites while they're in eclipse. Things that we thought were minuscule, in the end you can't see them within this technique. But you cannot invent them. There has to be some physics behind it. And in terms of the troposphere, it's not so easy to differentiate the physics of one part and the other part. We can...
Why error bars in that graphic from the GPS are so different? Goes from 0.5 to 3, though error bars from radiometers seems to be more or less the same. I mean, those error bars are different from the GPS. Yeah, the radiometer are more or less similar, but no, this is GPS. This is not radiometer. This is GPS. Ah, okay. Ah, okay, right. Yeah. Okay. Yeah. Mm-hmm.
Well, first of all, thank you very much for the very nice talk. I was fascinated by the stability of the water vapor that you showed on the second to last slide, I think. And I appreciated that comment to both sides, La Palma and Monarchia. I was wondering, what's the cause for this stability? Can it have anything to do with the cut in the beginning of the 2 hours? Is it a real effect?
These values are average values. Of course, you can have a change in the temperature of water by vapor in both directions. Okay? In just 2 hours, the temperature.
In terms of water vapor are in winter time, so this is something that is somehow surprising at least. The reason you have explained very well, so in winter the temperature is lower, and this is also the reason why the model, the first plot he showed, that Begoña showed, there was a spectra taken by Matt Mountain here at Isaña with the model on top. These models were very old models, and at that time the temperature was not taken into account, and the discrepancy comes from the fact that this model was wrong. Now, if the model would be a good model, taking into account all the parameters of the atmosphere, the match would have been better. Right. But going back to this surprising result, you have gone to look for good conditions, right? So precipitable water vapor better than 3, which is the standard supposed to be good. Would it be possible to use the result to estimate which is the useful time at the observatory in terms of the cloud? Yes. But, I mean, you have a threshold. I mean, because this result is surprising by 2 things. First, it's better in winter, and also we know. All right. Okay, but also we know that winter and spring are the worst in terms of useful time. All right. So we know that in winter and spring we observe less percentage of the time than in summer. Okay. Then, I wonder, you have put the threshold in 3 millimeters. Couldn't you play with a higher threshold and try to match the percentage of nights with a value higher than, I don't know, whatever, and try to correlate that with in situ measurements of useful time? Because if you could do that, it could be very, I mean, I understand it is not easy, but it's not easy to know this parameter in any other way. This is a value, this is impossible to know.
I try to correlate this data with the database to select photometric night and see if there are any correlation between photometric and non-photometric conditions, collecting the physical observations, and I get more or less the similar statistical values. Well, no, not such the same statistical value. I have the same number of data for any month to calculate the physical observation. The statistic is lower, of course. I get the result, the acceleration of the
Yeah, but that was not my question. My question was more simple than that. Forget the photometric or not photometric. A particular night, the telescopes are closed because there are clouds. So, how do we know that? Because they put in the log, we are closed because there are clouds. And then you go to the log of the GPC, to the log of the Isaac Newton telescope, to all the logs of the observatory, and with this information, which is processed on top of that, you estimate the percentage of time lost due to poor weather is that one. So I wonder, would it be possible to define which would be the most likely value that you can estimate and try to correlate with this other value provided by the tables of the telescope, and then to get an independent estimation of the night in which you will not be able to open the telescope because of the weather?
No, because I have a night, not photometric condition, that means you have clouds or zeros or something that have bad precipitable level. So, that less than 3 millimeters or even 10 millimeters. So if you don't have clouds and you have 10 millimeters, maybe, I don't know, you have all the options. This is because I say no. Maybe I want to study more this problem. Sorry? Yeah. All kinds of values. Because the clouds are only a fraction of the whole atmosphere. So you can have precipitable water vapor distributed in all the columns, or you have a larger precipitable water vapor. So you have all the options. I don't know, maybe I can. Yeah. select the photometric condition that are assume the other parameters because you have a lot of parameters to decide if the telescope is open or not. For example, that, wind, how I can have a vision of the wind here. In that case, yes, but it's not so simple because you have to set the law by hand, and that's not. This is the reason because I select the Canfield database just to have a reference of the photometric or not photometric. I assume if the night is photometric, I have good conditions. They can't be more open. So. Yes, but this is only one parameter, and there are a lot of. But for the moment, no one of our telescopes closed because of the precipitable water vapor. Because, well, only the related humidity, yes. But this can be. Basically, that's a 1 to 5 micrometer, the conditions are that. We are waiting for that concept. I don't know why. I think it's very clear that we will try to do that, and it's a logic and tradition with the more amazing you must select the local. Yes, I'm sure that this data was taken to the region. So if you try something like that in summer, what is it?